Okay, so you have for number 17, okay, we have, we're looking at rational expressions. Okay, and here we have, starting out, we have x squared minus 9, and we have all over x squared minus 4x minus 21. And looking at simplifying the expression. Okay, so this will be done through factoring. And so we have with x squared minus 9. Okay, so this will factor to x plus and x minus 3. As for x squared minus 4x minus 21, okay, so we're going to have more weight, again, as we factor x squared out to x and x. Now for factors of negative 21, because the combination of the outside and inside products will be negative, this is going to signal that more weight will be given to the subtraction than to the addition. So we have negative 7 and positive 3. Again, negative 7 times 3 is negative 21. Negative 7 plus 3 is a negative 4. And if you notice, between the numerator and denominator, we have a common factor with x plus 3. So we can have those to cancel out. And the simplified form of the original ratio, okay, this will come out to x minus 3 all over x minus 7. Now there's another part that is asked for, and this is in what are referred to as restricted values. And for restricted values, okay, those are values that x will not allowed to be, will not be allowed to be, okay. And now for rational expressions, okay, for fractions, the bottom value cannot be equal to 0. So for x squared minus 9 all over x squared minus 4x minus 21, the denominator cannot be equal to 0. And again, from this trinomial, okay, so we have with x squared minus 4x minus 21, okay, so you have the factors. Once again, you have x minus 7 and x plus 3. Okay, let me mention, okay, so there are going to be two restricted values, okay, stemming from the factors x minus 7 and x plus 3. Now, x plus 3 canceled out, but it doesn't undo the restriction. In other words, cancellation does not undo restriction. And so for what is disallowed for x, it'll be those values that will cause the whole expression and thus each of the factors to be equal to 0. So we have for x minus 7, if x minus 7 cannot be 0, then we have that x cannot be 7. And we have also x plus 3 cannot be 0. So we're going to have that x cannot be equal to negative 3. And so we have with these two excluded values, okay, the excluded values will be the restricted values. And once again, those are going to be 7 and negative 3. Now, for what we have in the case of the next item, okay, we're looking at, again, the simplified version as well as the restricted values. Now we have a change up in the variable, but we have a bit of history to repeat where we have a difference of squares in the numerator with y squared minus 64, and we have a trinomial in the denominator where we have y squared minus 7y minus 8. For y squared minus 64, okay, so this will factor out to y plus 8 and y minus 8. And for y squared minus 7y minus 8, okay, we have y to factor out from y squared. And then we have factors of -8 that will add up to -7. Okay, one factor we're going to have at y minus 8, and the other one we have at y plus 1. And looking at the factored forms of the numerator and denominator, okay, we'll have y minus 8 to cancel. And so we end up with y plus 8 all over y plus 1. So for what we have here, okay, we had the reduced form. Now this is a reduced form, but it doesn't represent all of what we have in the original setup. We just canceled out y minus 8. But now in terms of what the variable y cannot be equal to, again, we cannot have y to be such that the denominator is 0 in value. So you have y squared minus 7y minus 8, okay, cannot be equal to 0. And again, we had the same two factors, y minus 8 and y plus 1. So the whole expression cannot be 0, meaning that the factors cannot be either. So y minus 8 cannot be 0, so y cannot be 8, and for y plus 1 not allowed to be 0, and we have that y cannot equal -1. So we're going to have for the restricted values, the amounts of 8 as well as -1. Now, in the crossover to what we have in the next group, okay, we're looking at simplifying and operating between rational expressions, and we're not looking at restricted values, okay, this time around. Now, for what we have in the case of number 28, okay, so we have 8x minus 3y we have all over x to the third times y to the fourth. And we have times 6x y to the eighth. And we have all over 24x minus 9y. Okay, and we're not going to have so much an active level of factoring since the greatest common factor of 8x minus 3y is 1, and there's no common factor between x cubed and y to the fourth as it stands, nor for 6 and x and y to the eighth other than the number 1. But we do have in the binomial, in the denominator, in the second denominator, okay, there is a common factor we can extract, and the highest term that will go into this difference of the x and y terms is going to be the number 3. So, and setting up what we have in the follow through. So we have 8x minus 3y over x cubed y to the fourth once again. And you have times 6x y to the eighth. And again, for 24x minus 9y, we can just go ahead and factor out 3. And we have times the quantity of 8x minus 3y. And so for what we have in the setup, okay, notice we have 8x minus 3y in numerator position from the first fraction, and we also have it in the denominator from the second fraction. So we can get these to go out. And if you notice, you have 6 over 3, and I can technically go ahead and reduce, but I will just do this in the next step. Okay, so you have 6x y to the eighth from what is left over at the top. And for what we have in combining what we have in the denominators, okay, we have 3x cubed y to the fourth. All right, so I have for 6 over 3, 3 will go into 6 2 times, and we'll deal with the variables at the next phase. Okay, so you have 2x y to the 8th all over x cubed y to the fourth. Okay, and okay, now for what we have here, you have 2, you have x, or x to the first, times y to the 8th, all over x cubed y to the fourth. And in terms of taking what we have and reducing, okay, if you notice, for what we have between x, okay, the higher degree in x is in the denominator. So I'm going to do with x, where the higher power exists, okay, the reduced form of that variable is going to be the location as well. So for x to the first over x cubed, I'm looking at x to the 3 minus 1. And for y to the 8th over y to the 4th, then we have y to the 8 minus 4. Again, taking the lower degree from the higher. And so we're going to have, for the end result here, we're going to have 2 times y to the 4th all over x squared. And that will be the final result in the case of number 28. All right. And now we have, in the case 41, okay, so we have a situation where we have fractions added together and consisting of the same denominator. Okay, so you have m squared over m plus 3, and we have plus 6m plus 9 over m plus 3. Okay, so again, the operation between the fractions is addition, so no multiplication, no division yet. All right, so we got the same denominator, and I can go ahead and combine the numerators. So we have m squared plus 6m plus 9, and we have all over m plus 3. And for m squared plus 6m plus 9. Okay, so we have, once again, a square trinomial. So this will factor. Again, this is going to factor to m plus 3 times itself. And we have all over m plus 3. So you have a trio of m plus 3 binomials. Okay, and we have for the interacting case, so we're going to get a set of m plus 3's to cancel out. So that means we have 1 m plus 3 remaining, which comes from the numerator. So the reduced form resulting from adding these ratios together is going to become m plus 3. All right, now in looking at what we have in dealing with operations, okay, between and among fractions, okay, and we have now the other day we looked at common factors, and we have say in the case of number 43, Okay, so we have 2 over 9c. And we have plus 7 over 15c to the third. All right. Now, in terms of taking what we have and factoring, okay, so we have for 9, if we're looking for prime factors, okay, now 9, you have 9 times 1, but you also have 3 times 3, and 3 is a prime number. And for 15, prime factors of 15 will be 3 and 5, so 15 we have 3 and 5. So we're going to have, again, we have with the variable factor, okay, we have c. And the least common denominator is going to be the higher or highest power of the variable factor or factors. Now for the prime factors, okay, so you have 3 and 5. And we're going to have for the least common denominator, okay, so with the prime factors of 3 and 5, okay, so 3 appears once from 15, but it's going to appear twice from 9. Okay, so you're looking at the highest degree, or looking on the basis of the greatest number of appearances of each of the prime factors. So in this case for 3 it appears twice, and from 5 it is going to appear 1 time. And with the variable factor c, we have c and c to the third, so again we go with the highest degree. So the least common denominator, we have 3 times 3 is 9, 9 times 5 is 45. So the least common denominator, okay, is going to be at 45c cubed and in adding the fractions together, similar to adjust, I'm going to adjust both 2 over 9c and 7 over 15 times c to the third in terms of the least common denominator. Okay, so we have a 2 over 9 times c. I'm going to multiply this ratio by the number of times that 9c goes into 45c cubed. So 9 goes into 45 5 times. And c will go into c cubed, c squared times. As for 7 over 15c cubed, okay, so you have 15 will go into 45 3 times. And we already have c cubed. C cubed goes into itself 1 time. So the second ratio will be multiplied by 1 in the form of 3/3. And so we have both denominators, 9c times 5c squared and 15c cubed times 3 will be at 45c cubed. And for the final result, we have 2 times 5c squared, so this will be 10c squared. And we have plus 7 times 3, which will be 21. And so we have for that result, again, we have 10c squared plus 21 all over 45 times c to the third. All right, now looking at what we have with 48. We have 4 over m minus 2 minus 3 over m. And the least common denominator, it will be the product of m and m minus 2. So you have m is its only standalone m factor, and then we have the binomial m minus 2. And so looking at what we have in the difference of fractions, and expressing both of them in terms of the least common denominator. So you have 4 over m minus 2. Okay, now we have the m minus 2 portion of the least common denominator, but we're missing the m. And we have minus. Okay, now we have 3 over m. So this one has the m factor, but it is missing m minus 2. Okay, so we have, again, so both denominators, okay, we have in the form of m times, okay, the quantity of m minus 2. Then we have 4 times m. We have bringing down the subtraction. And what I'm going to do here, I'm just going to add this added step, extra step, okay, so you have minus 3, and we still have distributing over m minus 2. And if you've gone ahead and distributed, okay, that's okay. I'm just adding another layer of exposition. Okay, so you have 4m, then we have negative 3m. And negative 3 times negative 2 is going to become positive 6. And again, we have all over m times, okay, the quantity of m minus 2. And we have in the final result, so we have 4m minus 3m becomes m. And we have m plus 6. And we have all over m times the quantity of m minus 2. Now, in the case of what we have with number 52, okay, so we have a trio of terms, okay, in the variable t, whereupon we have 5 over t squared, and we have plus 4 over t plus 2, and we have minus 3 over t, and in terms of what we have with the least common denominator, again, we have just the standalone variable terms. We have t and t squared, and now for the factor t and the least common denominator, we're going to take the higher degree representation, so that's going to be t to the second, and again we have the only binomial denominator with t plus 2, so the least common denominator, we're going to have it t squared times the quantity of t plus 2. And so looking at combining the fractions together, so I'm going to rewrite what I have here in terms of the least common denominator. Okay, so we have with 5 over t squared, okay, so we have the t squared factor, but we still have the t plus 2 left over. So I'm going to multiply by 1 in the form of, once again, the missing factor of t plus 2 divided by itself. And we have next, okay, so you have plus, then we have 4 over t plus 2. Okay, so you have the t plus 2 factor, and we have t squared to work with. Now for the last ratio, this is perhaps the trickiest part, because you have partial representation of one of the LCD factors. Okay, if you notice, okay, we have t, but that is only part of t squared, so you still have a degree in t left over. And furthermore, we have the t plus 2 factor from the LCD. And so for what we have here, okay, we have all of the denominators will be in terms of the least common denominator. You have t squared times t plus 2, t squared times t plus 2, and t times t is t squared, and you still have times the quantity of t plus 2. And looking at what we have among the numerators, so you got 5 and t plus 2, and if I go ahead and multiply out, so I'm going to have 5t plus 10, and I have plus 4 times t squared. Okay. And I'm going to take this last part, just a little bit of an added step, so you have subtraction, and you got 3 times t times the quantity of t plus 2 okay, so I have 5t plus 10 plus 4t squared, and negative 3t times t is negative 3t squared. You have minus 6t. Okay, we have all over t squared times the quantity of t plus 2. Okay, and now you can put the terms in the numerator, arrange them as you may like. Okay, but I'm just going to put these in decreasing degree order. So we have 4t squared minus 3t squared. So we have that difference. We have it t squared. And we have 5t minus 6t. So this will be a negative t. And we have in the mix, we have positive 10 as the only constant at the top. And so we end up at t squared minus t plus 10. And this will be all over t squared times the quantity of t plus 2. And this will be the final result in this particular problem. All right, and just for the next few moments, let's see what we get. With 1 over 40 plus 1 over 100 minus 1 over 18. So let's see what exact result we get, and also simplify from taking 1/40 plus 1 over 100 minus 1/18. Okay, tell you what, if we look at the prime factorization, and we have with 40, 100, as well as 18. Okay, so you have with the number 40. Okay, so if we break down in terms of prime factors, so we have with 40. You think of two numbers that go into 40, say you have 4 times 10, or 5 times 8, or 2 times 20 for that matter. Now 4 and 10, now again, prime factors are positive numbers whose only positive natural number factors will be 1 and the number itself. Now for 4, you do have 1 and 4, but you also have 2 and 2. And 10, not a prime number, because you have not only 1 times 10 to be equal to 10, but you also have 2 times 5. Now, in the case of 100, you can say we have 10 times 10. And for each of the 10s, again, we have 2 times 5, times 2 times 5. So you have 2 times 2 times 5 times 5. And as for the number 18, you can say we have 2 times 9. And 2 is a prime number. And as for 9, okay, we can break this down further to 2 times 3 times 3. So we have, looking for the least common denominator. So we have with the prime factors, okay, so you have 2, 3, and 5. And for the least common denominator, okay, so we have with the factors of 2. Okay, so 2 appears once from 18. It appears twice from 100. But the most frequent occurrence of 2 in the prime factorization will be where it appears 3 times from 40. And as for the number 3, it doesn't appear from 40, nor does it appear from 100, but it does appear twice from 18. And as for 5, okay, so it comes once from 40, twice from 100, and not at all from 100. Not at all from 18, excuse me. Okay, so we have, say, 5 times 5. And for what we're going to have here, so we have, you have 8, 3 times 3 is 9, so you have 72, and 5 times 5 is 25, and 72 times 25, this will come out to a big number with 1800. But still, okay, that is going to be the smallest number that all of 40, 100, and 18 will go into. And so, looking at what we have now, and we have, upon rewriting the fractions in terms of the least common denominator, so you have for 1/40th. Now 40 goes into 1845 times. So the first ratio will be multiplied by 1 in the form of 45 over itself. As for 1 over 100, okay, so you have 100 will go into 1800 18 times. So the next ratio will be multiplied by 1 in the form of 18 over itself. And we have minus 1/18. And 18 will go into 1800 100 times. Thus you have the last ratio multiplied by 1 in the form of 100 over itself. Now we're going to have all the fractions in the adjustment to consist of the denominator, 1800. So like the first ratio would be 45 over 1800. Next would be 18 over, make that 45 over 1800 plus 18 over 1800. And then we'll have minus 100 over 1800. And if we combine the numerators, so you have 45 plus 18 is 63. And we have in turn 63 minus 100 is going to be minus 37. And so for the combination that we have here, Okay, we're going to end up at minus 37 over 1800. And we will, again, intermittently look at working with rational expressions. Now, and we're going to cross over, making a transition from combining terms, simplifying terms, factoring terms at the moment, to working with equations. And so we have among the categories being what we have with conditionals, contradictions, and identities. Okay, and so for what we have here. Okay, now for a conditional, now a conditional is going to be, for our purposes here, conditional is going to be an equation with a limited number of solutions. It could be one solution, two solutions, but as long as you have like a finite number of solutions. And we can say that, for example, if you're looking at solving for x, and we'll go with something fairly basic. Okay, we'll say we have something like 2x plus 5 is equal to 17. Okay. So if I'm looking at solving for x, okay, what I'm going to do here is I want to get the x term by itself and take care of any residing coefficients. So I have a single x term on the left, okay, and to get the left-hand side in terms of x only, I'm going to have to take care of the 2 as well as the 5, and so I can initiate the process by taking away 5 from both ends. So left-hand side we have a 2x, and to the right we have 17 minus 5, which will be at 12. And then undoing the multiplication by 2, by dividing both sides by 2, it's going to follow that for 2x over 2. Okay, this comes out to the desired x, and 12 divided by 2 is 6. So you have a limited number of solutions with only one solution, with that x is equal to 6. Okay, so this again is a case of a conditional. So you would have that 2x plus 5 is equal to 7 to ring true on the condition that x is equal to 6. Now, in the next category where we have a contradiction. Now, a contradiction is going to be an equation that has no logical solution. Okay, so you're trying to avoid inconsistencies. Okay, and let's say that if you're looking at, let's say, once again, trying to solve for x, And we'll say that we have 2 times, okay, the quantity of x plus 3. And say we have minus 4 is equal to x plus x minus 5. Okay, so you're looking at the value or values of x, okay, where both sides of the equation will be equal. Now, if I take care of, first of all, the parentheses on the left, so distributing 2 all over the quantity of x plus 3, I'm going to have 2x plus 6, and we have minus 4, and we have with x plus x minus 5, x plus x becomes 2x, we have minus 5, and then we have 2x, once again on the left, and plus 6 minus 4 is going to be plus 2, and again we still have 2x minus 5, and if you notice we have the same weight in terms of the variable terms on both sides, and if I join them together, so if I subtract 2x, let's say on both sides, okay, so you have complete cancellation, and left standing will be 2 numbers that are said to equal each other when in fact they are not. Okay, so there's nothing in x that we can do to rectify the situation. Okay, we did the correct algebra, and the variable terms wound up canceling each other out, and left standing are numbers said to be equal to each other when in fact they are not. And so we have, in effect, since there's nothing in x positive, negative, or 0 that can make both sides of this equation equal to each other. So in effect, okay, we have no solution. And again, this is a case of a contradiction. Okay, so conditional has a limited number of solutions. Contradiction has no logical solution. Now, for an equation that results as an identity, okay, so an identity will be an equation that has an infinite number of solutions. And we'll say that we have, for instance, okay, something that can lead up to an identity. And say we have solving for x. And we'll say that we have 3 times the quantity of x plus 4. And we have is equal to x plus 6. And we have 2 times the quantity of x plus 3. Okay. So for what we have here on the left, so we have 3 times the quantity of x plus 4. So we have equal to x plus 12. And then we have to the right, we have x plus 6. And distributing 2 over the quantity of x plus 3, okay, we have 2x plus 6. Again, we have 3x plus 12, and to the right we have x plus 2x, which will make 3x. We have plus 6, so this would be plus 12. And if you notice, okay, we have same terms on both sides. And if we were to unite the variable terms, they're going to end up canceling each other out. And for what is going to remain will be 12 on each side. So you have 12 is equal to 12. Now we have two numbers that are said to be equal to each other. In this case, that statement is going to be true. And what this is going to signify is that you have x, it could be 0, it could be a positive value, or it could be a negative value. And anything you plug in for x, you're always going to have both sides to end up equaling each other. And so we're going to have an infinite number of solutions. And the way you can express this, you can see we have all real numbers. Or you can also symbolically write, okay, with just the capital R in reference to all real numbers. And probably the most common notation we'll be looking into will be interval notation. And it'll be just like those numbers running between negative and positive infinity. So these are three different ways of saying the exact same thing. So we're just looking at referencing all real numbers like positive numbers, negative numbers, 0, fractions, radicals, reducible fractions, irreducible fractions, that sort of stuff. And so again, this is going to be yet another case of what we have with an identity. Okay. Now, in the case of equations, now the ones we looked into were first degree in the variable x. Now, looking at sort of tying in what we have had with factoring and the FOIL method, looking into second degree equations, and we have in the next realm, okay, we have for quadratic equations, now for a quadratic equation, and we have by definition now a quadratic equation is going to be a second degree equation whose standard form again, whose standard form, okay, we're going to have at ax squared plus bx plus c is equal to 0, okay, whereupon a does not equal to 0. And what I mean by second degree equation, and again, we have just for the variable of concern, the independent variable we have at x, so second degree is in reference to the power 2. And if we had a equal to 0, this term would vanish and you would no longer have a second degree equation. Now, for quadratic equations, okay, there are various techniques that can be utilized, just given the type of coefficients involved. And we have one common approach is going to be the zero product property. And this property states that if we have at least two expressions, again, not limited to two expressions, but say we have two expressions, a and b, and they multiply out to 0. For this to be true, then at least one of these factors has to be 0. So for the product to be equal to 0, in other words, for a times b to be equal to 0, one of these must be 0. And in terms of what this has in terms of the quadratic equations, in other words, what's this got to do with the quadratic equation? And we can take just as examples here, and we can say that in solving for x, and we'll say that we have let's say we have x squared plus 7x plus 12 is equal to 0. And just looking at what we have here, so you're looking at the values of x such that x squared plus 7x plus 12 is equal to 0. And if we look at factoring, so from x squared we have x and x. Now for factors of 12, that will add up to 7. So you have plus 4 and plus 3. And you might be wondering, okay, where did I see this before? This is back when we were looking into the restricted values. Okay, so this in a way was the zero product property, but we were looking at what was disallowed in x from being equal to 0, and also what was disallowed in y from being equal to 0 from those first two problems. But now we're looking at solving, okay, upon setting equal to 0. So we have if x plus 4 is a 0 factor, we have x plus 4 is equal to 0, and from this, okay, we want to have x equal to negative 4. And if, on the other hand, we have that x plus 3 is equal to 0, we're going to have that x is equal to negative 3. And you can always go back and check your solutions. We have negative 4. Now, if we have x at negative 4 squared is going to be a positive 16. 7 times negative 4 is a negative 28. So you got 16 plus negative 28 will be negative 12. Negative 12 plus 12 is 0. Now for negative 3 squared is 9. Now we have 7 times negative 3 is negative 21. 9 minus 21 is negative 12. And in turn, negative 12 plus 12 is equal to 0. Okay. And so we have, again, this is another case of a conditional, where this equation is true on the condition that x is either negative 4 or negative 3. And let's say that we have as a second case, and let's say we have an equation that is quadratic, but it is not yet in standard form. And we'll say that we have for this one, okay, we say that we have x squared plus 36 is equal to 12x. Again, you're looking at the values of x such that x squared plus 36 is equal to 12 times x. Now, if you notice, this equation is not set up in standard form, that is where it is equal to 0. But we can make a quick fix of this. Now the highest degree term is x squared, which is on the left. And what we can do is that we can form a trinomial in descending degree order if we just move the 12x over. And we're going to have in the rewrite, okay, so we're going to have x squared minus 12x plus 36 is equal to 0. And looking at factoring, from x squared I have x and x, and then factors positive 36, that will add it to negative 12. Well, guess what? It turns out that this is a squared trinomial, since we had the same binomials factored out with x minus 6 and itself. So you're going to have, in the result, you have a repeating factor. So we have only one x factor to result. And if we set this to 0, it's going to follow that we have x is equal to 6. And checking out, 6 squared is 36, plus 36 is 72. And simultaneously, 12 times 6 is 72. And 6 will be the only solution that will cause this equation to ring true. Right. And so just one more case here. And just want to mention in terms of how to go about, let's say if you have an additional coefficient. And let's say that if we have so you have negative 2x squared plus 8x plus 64 is equal to 0. One approach, say if I want to work with just x squared, I can factor out the negative 2. So we have negative 2 into negative 2x squared, so this will be x squared. Negative 2 into 8x, so this will be a minus 4x. And negative 2 into positive 64, that's going to be a negative 32. And we have negative 2, and we have with the trinomial resulting in the reduction. So x squared, we have x times x, and factors negative 32, that will add up to minus 4. Okay, more weight is going to be given to the subtraction than to the addition. So you have x plus 4 and x minus 8. And in terms of our x factors, now negative 2 is just like filler. It's not doing anything with x in terms of the basic operations. It's not adding, subtracting, multiplying, or dividing x. So this is just kind of like a dummy factor. It's not doing anything for us in terms of solving for x. But last two expressions, okay, we do have an x. So we have x plus 4 is equal to 0. We also have x minus 8 is equal to 0. And if x plus 4 is equal to 0, so we have x equal to negative 4. And for x minus 8 equal to 0, we have the x is equal to 8. And you can always go back and check, and those will be the solutions. And I'm just going to mention, I'll just give a slight reworking of this. Just creating a very slightly different pathway. So if I were to just divide by the leading coefficient, negative 2, so if I divide the equation by negative 2, what's going to happen here is that we would have x squared minus 4x minus 32 is equal to 0. And you'll still have the same binomial factors. And once again, just setting each of these equal to 0. You still have x at negative 4 and also x at positive 8. And both approaches are viable. And you still get the same result. And there are other techniques in terms of solving equations, and we're going to be looking into those for next time. And just items to go ahead and be looking into. Again, along with the first Alex set. Okay, now not to be turned in, but just kind of look into, kind of do a little prep for next time. Okay, we have from page 68, number 24, 26, 28, 30, 34, 35, and rounding out the rest, they have 40, 41, and also number 64.